Ever stop and think about the phone in your pocket and then picture one of those massive, room-sized supercomputers, the ones you see in movies? They seem like they're from completely different planets. But what if I told you they share some deep architectural secrets? Well, today, we're going to pull back the curtain and see what makes them both tick.
Right? It's a fantastic question to kick things off. One of these things fits in your hand, and the other can literally predict the weather for an entire continent. But as you're about to see, the core ideas, the fundamental principles behind how they're built, they're surprisingly similar. It really all just boils down to organization.
So to get started, we're going to do something simple. We're going to look inside just one computer. Because once you understand the basic parts, the building blocks, we can then see how those same ideas get scaled up, way up, from the smallest gadget to the biggest machine on Earth.
Okay, now, this should look pretty familiar to a lot of you. Right at the heart of any personal computer is the CPU, the central processing unit. That's its brain. And it works with memory and storage. Then, of course, you've got all the other bits and pieces that let it talk to the outside world. The ports and controllers for your monitor, your keyboard, the internet. Think of this as our basic blueprint.
Now let's pivot to your phone. See, the core stuff is exactly the same. You've got a CPU, you've got memory, but the way it interacts with the world, its input and output, or I/O, that's where things get really different. Instead of a keyboard, you've got a touchscreen. Instead of just an Ethernet port, you've got a cellular modem, Wi-Fi, GPS. The fundamental design is the same, but the parts are totally customized for its job on the go.
So what about a beast like a mainframe? Well, believe it or not, it's the same story, just on a whole different level. Multiple CPUs, tons of memory, but check out that third bullet point, a specialized I/O channel system. That's the key. It's built for a completely different kind of work, handling just insane amounts of data for huge companies. Same concept, just absolutely supercharged.
So how do all these different pieces actually talk to each other? Well, this image shows it perfectly. We're looking at a motherboard, which is really the foundation of the whole system. The best way to think about it is like a city map, with all the roads and highways connecting everything, the CPU, the memory, all the ports, so they can all communicate instantly.
And all this talk of connection brings us to a really important idea: synergy. This is the secret sauce, really. I mean, a super fast CPU is great, but it's pretty useless if it's waiting around for slow memory. When all these components are designed to work together perfectly, the whole system becomes way more powerful than you'd expect, just by adding up the parts.
Right, so that idea of everything being connected is absolutely key. So for this next part, let's zoom in on that. We're going to look at how information actually moves around inside the machine. We're talking about the data superhighways.
So, there are basically two main approaches to moving data around. On the left, you've got bus architecture. This is what's in your PC and your phone. Think of it like a shared city street, where all the data from all the different components travels along the same pathway. Now, on the right, you have the channel architecture from those big mainframes. This is less like a public road and more like having a dedicated logistics company with its own fleet of trucks. It has a separate processor just for managing data, freeing up the main CPU to do other things.
And what's cool is that you use these data highways constantly, probably without even realizing it. I mean, every time you plug in a flash drive, you're using USB. That powerhouse graphics card that runs your games, it's using a super fast internal highway called PCI Express. And your main hard drive is shuttling files back and forth using SATA. These aren't just technical terms, they're the physical roads that make your digital life happen.
And why does any of this matter? Well, the design of these highways has a huge impact on your experience. For example, have you ever wondered why your video calls are usually so smooth and not a stuttery mess? It's thanks to really clever technologies like isochronous data transfer. It's a fancy term, but it just means the system guarantees that your audio and video data arrive in perfect, regular chunks, keeping everything in sync.
But here's the thing, even the most perfectly designed, synergistic single computer will eventually hit a wall. There's just a physical limit to how powerful you can make one machine. So, how do we get past that limit? Simple, we team up. And there are two main ways computers can team up. On one side, you have tightly coupled systems. This is what's happening inside most modern PCs. You have multiple processor cores inside one box, sharing everything. It's kind of like having several brains that all share one body. On the other side, you've got loosely coupled systems. These are totally separate, independent computers, each with its own stuff, but they're linked together to work on a common goal. Think of it as a team of individual experts collaborating on a project.
Okay, so let's really dive into that loosely coupled idea. We're going to focus on the most popular way to create incredible computing power from separate machines, something called clustering.
So what is a cluster? At its core, it's just a team of computers. Each individual computer is called a node, and it's a complete system all on its own. But with some very clever software, they're all configured to work together. And the magic is, to the outside world, they look and act like one single massive, super powerful machine.
So why go through all this trouble? Well, there are 4 huge advantages. First, obviously, is raw power. But second, and this is absolutely crucial for things like cloud services, is fault tolerance. If one computer in the team fails, the system detects it instantly and its workload is automatically shifted to the other healthy nodes. You, the user, never even notice a hiccup. This is what gives us high availability and allows for something called load balancing, where huge jobs get broken up and spread across the whole team.
And this is what it actually looks like inside a data center. These are often called Beowulf clusters. On the left, you can see a single blade server. That's an entire computer packed onto one slim board. And what you do is you take dozens or even hundreds of these, which are often built from regular off-the-shelf parts, and you just slot them into a rack like the one you see on the right. And just like that, you've basically built a supercomputer on a budget. It's pretty amazing. But let's think bigger. What if we could take this idea of clustering and just blow it up? What if the team wasn't just in one rack or even one building? What if the team could be global? Well, that's exactly the idea behind something called grid computing. It's a technique that finds all the spare, unused processing power from thousands, even millions of regular computers all connected to a network like the internet, and it pulls all that power together to work on one single enormous problem. It is the ultimate team-up, turning the entire internet into one potential supercomputer. And one of the most famous and, frankly, coolest examples of this is the SETI at Home project. It takes this giant fire hose of data coming from radio telescopes and breaks it into tiny, bite-sized chunks. Then, it sends those little chunks out to over 500,000 volunteers all around the world. Their home computers analyze that data in their spare time, when they're not being used, all to help in the search for extraterrestrial intelligence. It's just a beautiful example of global collaboration. So, there you have it. We've gone from the tiny chips inside a single phone all the way up to a global grid of computers all working as one. It really shows a fundamental truth. If you understand the basic building blocks and figure out clever ways to connect them, you can scale computing power almost infinitely. And that leaves us with a pretty massive question, doesn't it? With this incredible collaborative power literally at our fingertips, what's the next great problem that we should solve together?